The first 100 days on Mars will not be about flags or footprints. They will be about one question. Can humans actually stay alive on a planet where the air cannot be breathed, the dust gets into everything, and one mistake can turn fatal fast? And if the base is still running by day 100, then humanity has done more than land on Mars. It has started learning how to live there. The first 100 days on Mars begin with the most dangerous part of the entire mission, the landing. You hit the top of the Martian atmosphere at about 12,100 miles per hour, and from that point you have around 7 minutes to go from interplanetary speed to a complete stop on the surface. That is why engineers call it a high-risk phase. Everything has to happen fast, in the right order, and with very little margin for error. The problem is simple to describe and very hard to solve. Mars has an atmosphere, but it is not thick enough to do the job the way Earth's atmosphere would. It is thick enough to create extreme heating and violent shaking as you come in, but it is too thin to slow a heavy human landing vehicle safely by itself. So you do not get the benefit of a full atmospheric braking system, and you do not get the simplicity of landing in a vacuum either. You get the worst combination. The planet fights your descent, but it does not help enough. That means your spacecraft has to survive heating, stay stable, deploy the right systems at the right time, and find safe ground while moving through an atmosphere that is weak, unpredictable, and not very forgiving. If a heat shield performs below spec, that is serious. If the parachute timing is off, that is serious. If radar lock is delayed, that is serious. If the engines do not throttle correctly near the surface, that is serious. You're dropping toward a rough terrain, and the sequence is so compressed that a small problem can become a mission-ending problem very quickly. And here is the harder part. Once the landing starts, nobody on Earth can step in and save you. That is one of the first things Mars changes. The communication delay is too large for real-time control. Depending on where Earth and Mars are in their orbits, a signal can take more than 20 minutes to travel one way. At maximum separation, the round trip can be around 44 minutes. So by the time Mission Control sees your descent data, the landing is already over. They are not flying you down live. They are receiving a delayed record of what already happened. That changes the whole meaning of support. On earlier missions close to Earth, ground control can guide, advise, troubleshoot, and react quickly. On Mars, that model breaks down at the exact moment when the danger is highest. If a thruster misfires, Earth cannot correct it in time. If your guidance software sees a hazard and changes the landing point, that decision is made on board. If there is a serious anomaly during descent, the people on Earth will know about it only after the outcome is already fixed. So your first contact with Mars is also your first lesson in isolation. This is the first human frontier where help does not come quickly and even expert advice arrives late. Call Houston still exists, but now it means something completely different. It does not mean someone is about to rescue you. It means you are reporting your situation to people who are too far away to act in the moment. The spacecraft, the software, and the crew have to handle the landing alone. Now suppose the landing works. The engine's cut off, the vehicle is down, the structure holds. Is the dangerous part over? It has only changed form. Touchdown on Mars is not the point where the mission becomes safe. It is the point where permanent exposure begins. The surface pressure on Mars is usually around 6 to 10 millibars. That is roughly 1% of sea level pressure on Earth. The atmosphere is about 95% carbon dioxide. Oxygen's only a tiny fraction of the air. Those numbers tell you something very direct. Mars is not a place where your body can tolerate even a short mistake. There is no version of stepping outside for one quick task. There is no version of opening something for a second and dealing with it later. There is no version of taking a risk because it will only be a brief exposure. Your body cannot breathe that air. Your lungs cannot use it. The pressure is far too low. A suit leak is serious immediately. A bad seal is serious immediately. A cracked visor is serious immediately. A failed airlock cycle is serious immediately. That is one of the biggest corrections Mars forces on you. From a distance, it looks like a landscape. There is a sky, a horizon, weather, dust, valleys, and open ground. but the physics are much closer to space than to Earth. The fact that Mars looks like a whirl can trick your instincts. It feels like a place where, in an emergency, you might run outside, grab something, and come back. You cannot. The environment gives you almost no buffer at all. So what do you actually do first after landing? Not exploration, not celebration, not the kind of dramatic first mission moments people usually picture. Your first job is to prove that your hardware can keep you alive for the next hour and then the next one after that. The first day is dominated by checks. Power comes first because every major system depends on it. Pressure integrity comes first because the habitat is your breathable environment, your medical safety margin, and your only real shelter. Life support comes first because if oxygen delivery, carbon dioxide removal, humidity control, and temperature regulation are unstable, everything else becomes secondary. You also have to inspect for dust intrusion, verify structural condition after landing, confirm thermal performance, validate communication systems, and compare the actual landing site with the orbital maps and hazard models used before arrival. This sounds procedural, but on Mars, procedure is survival. Every sensor reading matters, every seal matters, every connector matters, every watt matters. A small issue that would be inconvenient on Earth can become a mission priority on Mars because replacement parts are limited, repair windows are limited, and immediate backup help does not exist. In the first 24 hours, the crew is not trying to do something historic in a symbolic sense. The crew is trying to confirm that the entire system works as a closed life support chain on another planet. That is also the moment Mars stops being an idea and becomes a machine problem. Before landing, Mars is still a destination. After landing, Mars is a list of hard requirements. Can the habitat hold pressure continuously? Can power remain stable through the first night? Did dust get into critical interfaces during descent? Are the environmental systems performing at the numbers they were supposed to hit? Are the suits still clean and ready? Is the landing site safe enough for the first movement outside if that becomes necessary? Those are the real opening questions, and the first success on Mars is smaller than most people expect. It is not planting a flag, it is not taking the first step, it is getting through the first day with all critical systems stable. That sounds less dramatic, but it is more important. If the habitat holds pressure, if life support stays nominal, if the power system behaves, and if the crew confirms that the landing did not quietly damage something vital, then humanity has done something completely new. It has kept a human system alive on a planet that does not naturally support human life. That is why the first day matters so much. Mars is not conquered by arrival, it is handled 1 hour at a time. The real achievement is not reaching the surface. The real achievement is making the next hour possible, and then doing it again and again until survival starts to look like a routine. But the next problem starts immediately after that, and it is even more basic. Once you're down safely, Mars takes away one of the assumptions you have lived with your entire life. Air stops being something around you and becomes something you have to manufacture, protect, and count, minute by minute. Mars has weather, clouds, seasons, and a day almost as long as Earth's. None of that means you can breathe there. That is the first thing Mars takes from you once you are on the surface. It takes away the normal meaning of air. A lot of people picture Mars as a harsher version of Earth. Cold, dry, dusty, but still, basically a place where a human could maybe push through with enough courage. That picture falls apart the moment you look at the numbers. Mars rotates once every 24.6 hours, which feels familiar. It has winter and summer. It has polar caps. It has wind. It has dust storms. It even has clouds. So at first glance, your brain wants to classify it as a world that is difficult but still world-like in a human sense. But the atmosphere changes everything. The surface pressure on Mars is usually only around 6 to 10 millibars. That is not just thin air. That is air your body cannot use. On Earth, pressure is part of the system your body depends on every second without you noticing it. It helps keep normal breathing possible. It helps keep fluids behaving the way your body expects. It is part of the reason your lungs work the way they do. Mars has enough atmosphere to move dust, shape dunes, and create weather patterns. It does not have enough atmosphere to support a human body. That makes Mars dangerous in a very specific way. It looks more familiar than it really is. You see open ground and a sky overhead, so some part of your brain still wants to treat it like a landscape. But it is not a landscape you can enter directly. It is a hostile environment that only looks like one. And in the first days on Mars, that becomes one of the biggest mental adjustments. You stop judging the planet by appearance and start judging it by pressure, gas mix, and survival time. So then what actually lets you go outside at all? Not bravery, not training alone, a machine wrapped around your body. That is why your suit stops being something like clothing and becomes something much more serious. On Mars, a suit is not gear in the casual sense. It is a portable life support system doing the jobs the planet refuses to do for you. It provides pressure. It gives you oxygen. It removes carbon dioxide. It helps control temperature. It carries cooling and water systems. It shields you from dust, radiation exposure, and extreme swings in heat and cold. Without it, you are not uncomfortable. You are in immediate danger. That lesson becomes constant during the first week. Every time you leave the habitat, the same fact is reinforced. You're not stepping out into nature with protection layered on top. You're stepping into an environment where your suit is performing basic body functions the outside world cannot support. In practical terms, that means your suit is closer to an external organ system than to armour. It is maintaining the pressure your lungs need. It is maintaining the gas mixture your blood needs. It is helping manage heat your body cannot dump into the Martian environment the way it does on Earth. It is keeping fine dust out of the places where one bad contamination event can become a systems problem. And this changes how you think about movement. On Earth, walking outside feels like freedom because the environment itself carries most of the load. On Mars, the environment carries almost none of it. Your freedom is limited by tanks, filters, seals, battery life, temperature control, and the condition of every connector between you and the habitat. If your suit fails, Mars does not give you any backup. There is no breathable air to fall back on. There is no pressure margin to rely on. Every step outside is only possible because you brought your own controlled environment with you. But even that is not the full trap, because Mars does have oxygen in the atmosphere, just nowhere near enough and not in a way that helps you. That detail matters because it shows how misleading Mars can be. The atmosphere near the surface is mostly carbon dioxide, so about 95%. The rest is mostly nitrogen and argon, with only a tiny fraction of oxygen, and even a small amount of carbon monoxide mixed in. That is not a technical curiosity. It tells you exactly what kind of planet Mars is. It's a planet with air in the visual sense, but not in the human sense. There is almost no usable oxygen, almost no pressure support, and far too much carbon dioxide for human breathing. So even the fact that oxygen exists there becomes part of the illusion. The word is present, the function is not, and that creates one of the deepest changes in the first 100 days. You stop thinking of the atmosphere as something you live in, and start thinking of it as raw material. On Earth, air is the background of life. It is something your body uses automatically. On Mars, the air becomes feedstock. It is something machines process. It is something you analyze, compress, filter, and maybe turn into oxygen with the right hardware. The Martian sky is not there to support your lungs. It is there to be used by engineering systems. That shift matters because it changes how you think about survival. You no longer ask, "Can I breathe out there?" The answer is already no. The real question becomes, can my systems turn part of that atmosphere into something useful before my stored reserves run low? That is a very different relationship with a planet. It means the air around you is not comfort. It is inventory. It is a resource problem. It is chemistry. And once that sinks in, another hard truth follows right behind it. Mars looks huge, but your actual world is very small. That is one of the strangest parts of the early mission. You are standing on an entire planet with enormous canyons, giant volcanoes, wide plains, and horizons no human has ever seen with their own eyes. But the space where you can actually live is tiny. First, it is the habitat. Then it is the airlock. Then outside it is only the inside of the suit. Your safe environment keeps shrinking the closer you get to the open surface. That is where the psychological pressure starts building. The planet looks open, but your life depends on a very small sealed volume. Your blood works normally only inside that protected space. Your lungs work normally only inside that protected space. Your brain stays supplied and functional only inside that protected space. The surface may stretch for thousands of miles in every direction, but most of it is not accessible in the normal human sense. It is visible, not livable, and that changes the meaning of arrival. On Earth, arriving somewhere usually means your options increase. On Mars, arriving means the scale of the danger increases faster than the scale of your freedom. You now have a whole planet outside, but almost none of it can sustain you directly. That is why the first 100 days feel so different from the fantasy version of Mars. You did not come to a place where you can simply begin living. You came to a place where life only exists inside systems you brought with you. That is also why Mars can feel more mentally deceptive than open space. In deep space, the threat is obvious. Nobody expects to step outside without protection. Mars gives you sky, ground, weather, sunlight, and distance. It looks close to being a world you could enter normally, but it is not close enough, and that almost is one of the most dangerous parts. It can tempt your instincts to treat the planet as more forgiving than it is. By the end of the first part of the mission, that illusion is gone. Air is no longer something around you. It is something counted, stored, residued, monitored, and defended. The suit is no longer equipment. It is a portable survival system. The atmosphere is no longer comfort. It is chemistry. And the planet is no longer a wide-open frontier. It is a huge hostile surface surrounding a tiny human bubble. And once you accept that, the next problem gets worse. Because even if your habitat holds and your suit works, your own body is already changing. Mars does not just take away your air. Very soon it starts negotiating with your bones, muscles, balance, and every movement you make under 0.38 G. By the second week on Mars, another problem starts showing up, and this one is harder to see because it feels helpful at first. Gravity drops to 0.38 G. That sounds like a benefit. You feel lighter, you can carry more, you can move equipment with less effort. A load that would feel heavy on Earth suddenly feels much easier. For a moment, Mars can trick you into thinking your body has gained an advantage. But lighter does not mean safer. That is the mistake. Mars gravity is only about 38% of Earth's, and nobody has ever lived in that level of gravity long enough to know exactly what it does to the human body over time. We understand microgravity much better. We understand Earth gravity completely because it shaped us. Mars sits in the middle, and that middle is still a major unknown. So your first 100 days are not just about adapting to a new planet. They are also the start of a biological test nobody has ever run with real humans before. That matters because gravity is not just about how heavy you feel. It affects how your muscles work, how your bones stay strong, how your inner ear helps you balance, how blood moves through your body, and how your nervous system coordinates motion. So when gravity changes, a lot of systems change with it. Mars does not just lower the strain on your joints, it changes the rules your body has followed your entire life. And there is no guarantee that 0.38 grams is enough to keep those systems healthy for months or years. Then there is the next problem. You do not arrive on Mars with a healthy Earth normal body and then begin adapting from there. You arrive already weakened by the trip. That is one of the most important things people miss about a Mars landing. The journey itself has already started changing you before you ever touch the ground. During long spaceflight, bones lose density because they are not carrying normal weight. Muscles weaken because they are not fighting against full gravity. Even with exercise during transit, the body still comes into Mars under stress. So when you land, you're not starting fresh. You're starting after months of deconditioning. That changes the whole first month story. Instead of arriving ready for action, you arrive needing recovery. Instead of using the surface to prove what the human body can do, you first have to find out what the body can still do after the trip. The version of Mars where astronauts jump out of the lander, and immediately start moving like explorers in full control is not realistic. The real first weeks are much more controlled than that. Exercise becomes a major part of the mission almost immediately. Monitoring becomes routine. Rehab becomes part of the schedule. Mobility has to be relearned carefully, not assumed. And there is a hard reason for that. Mars gravity might not be enough to rebuild everything the journey cost you. That is the real concern. You're no longer in microgravity, so some systems may improve compared with the cruise phase, but you're still nowhere near Earth gravity. So you may recover part of what you lost while still continuing to degrade in other ways. That is why the early mission is so important scientifically. It is not only testing equipment and procedures, it is testing whether a human body can stop sliding downhill in 0.38 g, or whether that slope just becomes slower. That leads to the next surprise. Even basic movement stops feeling normal before your brain fully understands why. You feel lighter on Mars, but your mass has not changed. That is the key. A lot of people hear lower gravity and picture effortless motion, and in one sense that is true, but your body still carries the same inertia. Once something is moving, it still wants to keep moving. So the first few weeks can feel strange in a very physical way. You push off too hard, you misjudge a step, you swing a tool and it carries farther than expected. You turn with too much force. You stop later than you thought you would. That mismatch becomes one of the first real lessons of living in partial gravity. This affects almost everything. Walking changes, climbing changes, lifting changes, entering and exiting the habitat changes, going up a ladder changes, crossing uneven terrain changes, carrying gear changes. Even reaching for something at arm's length can feel different because your body is balancing under a set of conditions it has never known before. And on Mars, those small changes matter, because a stumble is not just embarrassing. It can damage a suit, contaminate equipment, waste time, or create a chain of problems during an EVA. So you do not just get used to it in a casual sense. You have to retrain movement very deliberately. Balance has to be relearned. Gait has to be relearned. Fatigue has to be relearned too, because lower weight does not automatically mean lower stress. Some tasks get easier, others get less stable, some motions feel efficient at first and then create mistakes later. The body and the environment are negotiating with each other, and the negotiation is not smooth. That is why Mars gravity is not a simple gift and not a simple burden. It changes performance in uneven ways. It helps you lift, but it can make control harder. It reduces the load on the body, but that can also reduce the stimulus your bones and muscles need to stay strong. It makes you feel agile right up to the moment momentum proves you are not as precise as you thought. In the first weeks, your mind keeps assuming Earth habits, and Mars keeps correcting them. And then you get to the hardest part of this whole section. We still do not know how much of this becomes stable, and how much becomes dangerous over time. That is what raises the stakes. We have data on microgravity. We know it can damage bone, muscle, cardiovascular function, and balance systems if countervailing measures are not strong enough. We know what full Earth gravity does because it is normal human life. But Mars gravity sits in the gap between those two, and gaps are where exploration gets very serious very fast. Maybe 0.38 g is enough to stabilize more of the body than expected. Maybe it is not. Maybe bone loss slows a lot. Maybe it keeps going, just more slowly. Maybe the cardiovascular system adapts well. Maybe it never fully settles. Maybe the inner ear and balance systems recover after landing. Maybe they stay slightly wrong in ways that affect work for months. And the uncertainty does not stop with adults. If humans ever stay on Mars long term, the question gets even bigger. What happens to development in 0.38 g? What kind of body does that environment shape over years instead of months? Would children grow differently? Would muscles, bones, circulation, coordination, and even the basic architecture of the body adapt in ways we do not expect? Right now, those are not solved questions. They are open questions. So during the first 100 days, your body is not just surviving a mission. It is becoming the first real evidence for an entire category of human biology. That is a huge shift in what Mars means. It is no longer just a place you visit with enough engineering. It becomes a place that forces your species to ask whether human life can remain fully human there in the long term, or whether the planet slowly reshapes what that even means. By week 2, that truth is already starting to show. Mars is not only testing courage, discipline, and technology, it is testing what kind of body can function on another world and whether ours is enough. And that gets even more serious when you remember that every hour this biological experiment is happening, another invisible threat is building in the background. You can feel low gravity. You cannot feel radiation, but radiation starts counting against you from day 1. Radiation starts counting against you on day 1, and one of the worst parts is that you cannot see it happening. Mars looks like a surface problem, rocks, dust, cold, rough terrain, but some of the most serious danger is not on the ground in front of you. It is passing through you quietly all the time. Earth protects you from a lot of this without you ever having to think about it. We have a thick atmosphere above us and a global magnetic field around us. Those two layers do a huge amount of work. They absorb, deflect, and reduce a lot of the high-energy radiation coming from space and the sun. Mars does not give you that kind of protection. Its atmosphere is very thin, and it does not have a global magnetic shield like Earth's. So the radiation environment is much harsher from the start. That matters immediately because radiation on Mars is not some rare emergency that only shows up during the unusual conditions. A significant part of it is always there in the background. While you are eating, sleeping, checking systems, fixing equipment, exercising, or planning the next EVA, dose is still accumulating. That is what makes radiation different from the dangers people usually focus on. Dust storms are visible, suit damage is visible, a pressure leak gives you a direct crisis. Radiation keeps working even when the day feels normal. And that changes how you think about the mission very early. You're not just trying to avoid big accidents, you're also managing exposure that builds hour by hour. If the total mission includes transit plus surface time, the exposure can become very serious depending on shielding and mission design. Even the surface alone adds to that total steadily. So from the beginning, Mars is not only testing whether you can survive obvious hazards, it is steadily charging a biological cost for every day you remain there. Now there is one important detail that makes this even more complicated. Landing on Mars does reduce some radiation exposure compared with staying out in deep space. But that does not mean the surface is safe. This is one of those situations where improvement can be misleading. Once you are on the ground, the planet itself blocks part of the sky and even the thin atmosphere provides some shielding. So yes, the surface is better than cruise in that specific sense. But better than deep space is a very low bar. It does not mean healthy, it does not mean acceptable without careful planning. It just means you're no longer getting the absolute worst version of the exposure environment. So the first 100 days on Mars would almost certainly be organised around radiation management from the start. Where do the crew sleep? What materials placed above or around those sleeping areas? How much water, cargo, or equipment can double as shielding mass? How thick are the habitat walls in the most protected areas? How long can the people stay outside before the added exposure becomes too expensive? How much shielding can local soil provide if you pilot around part of the habitat? These stop being side questions. They become daily operational questions. That is when radiation starts behaving like a resource problem. You budget it the same way you budget food, power, water and air. Every EVA is no longer just a surface task. It is an exposure decision. Every hour spent outside is not only a logistics calculation. It is a biological debit that cannot be taken back. Once that dose is received, it is part of the mission history of that person's body. And then Mars adds another layer of danger, because the background level is only half the story. The radiation environment can get worse fast. That is where solar storms come in. The steady daily dose is serious enough on its own, but solar activity can push the danger higher over a short period. When the sun throws energetic particles outward, Mars has very limited protection against them compared with Earth. That means a solar event can drive radiation levels upward fast enough that the mission has to respond immediately. This is not a slow planning issue anymore. it becomes a shelter issue, and that changes the function of the habitat. Most of the time, the habitat is where you live, work, eat, sleep, exercise, and maintain the mission. But during a major solar event, it becomes something much more specific, becomes a shielding structure. The crew moves to the best protected area, limits activity, and waits out the spike behind whatever mass and engineering the mission managed to bring. In that moment, the habitat stops feeling like a base and starts feeling like a storm shelter. That is a very different kind of life than most people picture when they think about Mars. You are not just monitoring the ground and the weather. You're also monitoring the sun, because events happening tens of millions of miles away can suddenly change how safe it is to remain in a certain part of your own habitat, or how long you can be outside. Mars is not only a local environment problem, it is part of a larger space environment that can turn against you quickly. And this is what makes radiation such an effective long-term threat. It works in two modes at once. First, it accumulates slowly in the background. Second, it can surge during solar events. So even when there is no dramatic emergency, the risk is still present. And when there is a dramatic event, the same invisible threat becomes more intense without giving you the kind of sensory warning humans rely on naturally. That leads to the hardest part of all. Radiation does not feel dangerous in the moment the way most other hazards do. There is no impact sound, no obvious damage pattern, no visible cloud moving toward you, no immediate pain that clearly tells you the problem has started. The threat is delayed, cumulative, and biological at a very small scale. It can raise long-term cancer risk. It can affect the cardiovascular system. It may affect the nervous system. It can interact with the rest of deep space stress in ways that are still being studied. That means radiation is not just one more hazard on the list. It is a multiplier. It sits in the background while every other strain on the mission is also happening. So by day 100, you might still feel functional. You might be productive. You might be walking, repairing equipment, doing science, following routines, and keeping the base running. And yet your radiation ledger has been growing the entire time. That is one of the most uncomfortable truths about Mars. A mission can look stable on the outside while invisible damage is still accumulating underneath the surface of daily life. This is also where Mars overturns another assumption. From far away, the planet looks like a geology challenge, a rough place to land, drive, drill, and explore. But some of its most serious effects are happening at the scale of cells and DNA. The planet does not need to hit you with one giant failure to be dangerous. It can simply keep exposing you day after day while you try to live normally inside a system that was never designed by nature to exist there. By the end of the first 100 days, that changes the emotional shape of the mission. You're not only surviving in a hostile landscape, you are living inside a radiation environment that keeps charging your body even when the day feels calm. Mars is not only hard because it is far away, it is hard because the price of staying there keeps rising even during your best days. And the next problem is more physical, more immediate, and much harder to keep out. Because while radiation passes silently through shielding and tissue, something else on Mars tries to get into every seal, joint, filter, and machine you depend on. Dust does not just cover the planet. It starts trying to enter everything. Dust becomes one of the biggest problems on Mars very early. And that surprises people because dust sounds minor compared with radiation, low pressure, and extreme cold. But on Mars, dust is not a cosmetic issue. It is a system problem. It gets on hardware, inside hardware, and eventually into every plan you make. At first, it is easy to underestimate it because on Earth, dust usually means dirt, mess, cleanup, maybe allergies. On Mars, it is much more serious than that. The particles are extremely fine, and they do not just fall off surfaces easily. They can cling because of electrostatic effects, and that makes them hard to shake loose once they get onto suits, joints, seals, tools, panels, and intake paths. So you stop thinking of dust as something you wipe away, and start thinking of it as something that keeps trying to attach itself to the systems keeping you alive. That matters because Mars missions depend on surfaces staying functional. Seals need to close cleanly. Radiators need to reject heat. Moving parts need to move without extra abrasion. Optical systems need to stay clear. Air handling systems need to stay as clean as possible. Filters need to keep working inside tight margins. Dust can interfere with all of that. It can coat, grind, clog, and infiltrate. It is small enough to behave like a constant nuisance and persistent enough to become a real maintenance threat. So one of the first major lessons on Mars is that the planet does not only challenge you with dramatic events like storms or radiation spikes, it also works against you with fine material that gets into the weak points of engineered systems. A big failure is easy to imagine. Dust is more difficult because it creates many small failures, and small failures can build into bigger ones. Then you learn something worse. The problem is not only mechanical, the chemistry matters too. Martian soil is not the same as harmless dry dirt from a backyard on Earth. Studies from Mars missions found chemicals such as perchlorate in the soil. That is important because perchlorates are not something you want inside a human habitat, inside food systems, or inside lungs. So the dust is not just troublesome because it is fine and clingy, it is also potentially toxic, which means contamination control becomes much stricter than most people first imagine. And this creates a very Mars-like problem. The same soil that may eventually help future crews make useful products through processing can also become dangerous if it gets into the wrong place. The same ground you may want to use as a resource is also the ground you do not want coating life support hardware or entering the living space. That means every airlock cycle carries some risk. Every EVA ends with the same concern. How much of the outside just came back in with you? So by the first weeks of the mission, contamination discipline becomes constant. You are checking suits, brushing down surfaces, controlling where tools go, protecting seals, watching filters, and trying to keep dirty zones separated from clean zones as much as possible. That is not overcaution. It is basic survival logic. If the habitat is the only place humans can live, then keeping Mars out of the habitat becomes almost as important as keeping air in it. And the dust does not just sit there waiting for you to touch it. It moves on its own. This is where the problem gets more serious. Mars dust is active because the atmosphere, even though it is thin, can still move fine particles over large areas. Dust devils form. Winds transport material. Local conditions change through the day. Instruments on Mars have shown that these dust features are not rare curiosities. They are part of the environment. Some dust devils can be large, fast-moving, and tall enough to remind you that even a thin atmosphere can still organize the surface into a very dynamic system. That changes how you think about the ground around the base. The dust is not just lying there waiting to stick to your boots. It can be lifted, carried, swirled, and redistributed. So even if you build clean procedures and clean routes, the environment keeps changing the contamination pattern around you. The surface is not static. The dust can come to you. Then there is another part of this that makes Mars dust even more unsettling. Under the right conditions, it can become electrically active. Grain rubbing against grain can create charge separation. That means dust devils and storms are not only transport events, they can also create electrical discharges. So now the dust is not just a dirt problem, a wear problem, or a contamination problem. It is tied to the electrical environment too. That matters because Mars missions depend on electronics, sensors, connectors, communication systems, powered mobility, and tightly controlled hardware interfaces. Once you are dealing with fine reactive dust plus electrostatic behavior plus possible electrical discharge, the challenge gets broader. You're no longer just asking how to keep hardware clean. You're asking how to keep hardware reliable inside a dusty environment that can physically, chemically, and electrically stress your systems at the same time. And this is exactly why dust becomes more serious the longer you stay. On day 1, it looks like an annoyance. By week 2, it looks like a maintenance issue. By day 100, it has become part of the architecture of survival. That is the real progression. At first, you think about cleaning, then you think about protection. Then you realize the mission has to be designed around dust from the beginning. Suit interfaces have to tolerate it, airlocks have to manage it, filters have to expect it, valves and joints have to survive it, Sampling systems have to work with it without spreading it everywhere. Optical surfaces have to remain usable despite it. Even the route between outside work and inside living space becomes part of dust control. That is why cleanliness on Mars is not about comfort or neatness. It is engineering. If dust keeps getting into the wrong places, seals wear out faster, moving parts perform worse, filters load up, heat rejection gets harder, visibility degrades, and routine operations start consuming more time and more risk. The crew then spends more effort protecting systems, which raises workload, which raises fatigue, which can lead to mistakes. So dust is not isolated from the rest of the mission. It pushes on the whole mission through maintenance burden. And the dangerous part is that it usually does this gradually. Mars does not need to destroy one major system in a dramatic instant to put the mission in trouble. It can do damage through accumulation. A little more contamination here, a little more abrasion there, a little less performance from one seal, one valve, one surface, one filter, one connector. None of those looks like a crisis by itself, but together they can move the whole base closer to one. That is one of the biggest corrections Mars forces on you. You stop thinking in terms of single big threats and start thinking in terms of persistent system pressure. Dust is part of that pressure every day. It gets on the suit you need for the next EVA. It gets near the hatch you need to trust. It gets into the airlock cycle you need to repeat hundreds of times. It gets onto tools, cables, sensors, camera lenses, mechanical joints, and the outside skin of the habitat. The planet keeps trying to come in as powder. By day 100, you understand the problem much more clearly. Dust is not background scenery. It is one of the main ways Mars interacts with everything humans bring. It turns the simplest tasks into contamination problems. It turns maintenance into a permanent mission function. And it forces engineers and crews to answer the same question over and over. How do you work on Mars without carrying Mars back into the only place where people can survive? That question becomes so central because the mission cannot avoid contact with the planet. You have to walk on it, drill it, move across it, sample it, and build on it. But every contact is also a transfer. Every transfer has a cost. And if those costs stack up long enough, dust stops being a detail and becomes one of the things that decides whether the base keeps functioning. And the next part gets even harder, because the atmosphere on Mars may be thin, but it still has enough force to shape the mission in ways that matter every single day. It cannot help you breathe, but it can still move dust, swing temperatures hard, and rewrite your schedule without warning. Mars may have weak air, but it does not have gentle weather. The weather on Mars looks mild if you only think about wind speed and thin air. It is not mild at all. In the first 100 days, weather becomes one of the main things controlling what you can do, when you can do it, and how much risk you take to do it. The first surprise is temperature. People hear that Mars is cold and think that explains it. It does not. The real problem is that Mars can change from relatively manageable to extremely dangerous very fast because the atmosphere is too thin to hold heat well. During the day, sunlight can warm the ground enough that conditions seem almost reasonable by Mars standards. Then the sun drops and the temperature can crash hard. Measurements from Mars missions showed this clearly. The surface can move from a few degrees above freezing in the daytime to deep extreme cold at night. That is not just uncomfortable. It affects almost every system you rely on. So in the first 100 days, temperature is not background information. It is an operational number. It affects battery performance. It affects how long equipment can stay outside. It affects how hard the habitat has to work to stay warm inside. It affects suit endurance, thermal control, and the amount of margin you have if something starts going wrong. A task that looks safe at one time of B can become much less safe a few hours later because the environment around it has changed so much. That means every plan has a thermal side to it. When do you go out? When do you come back? How cold will critical surfaces get? How much power will heating demand tonight? On Mars, those are not engineering details in the background. They shape the mission directly. And the cold on Mars is not simple because it is tied so closely to sunlight. That makes it easy to misread. If the ground warms under direct sun, You can start to feel like the environment is more manageable than it really is. But the atmosphere is still too thin to store and redistribute heat the way Earth does. So once sunlight changes, the surface can lose that warmth quickly. Mars does not stay stable for your convenience. It follows its own heat cycle, and your systems have to keep up with it. Then there is the next part that sounds weak on paper, but becomes serious in practice. The air pressure on Mars is very low, but the wind still matters a lot. That seems contradictory at first. If the atmosphere is only around 6 to 10 millibars, why care so much about wind? The answer is that Martian wind is dangerous less because of how hard it pushes on your body, and more because of what it moves through the environment. It lifts fine dust. It shifts particles across surfaces. It shapes dunes. It changes visibility. It affects contamination patterns around the base. It changes what gets carried into seals, optics, solar panels, radiators, and suit interfaces. So you are not looking at weather reports because you expect to be physically thrown around like in a storm on Earth. You're looking because the air is carrying material that can interfere with almost everything. That changes how the crew thinks about weather very quickly. A forecast is not just about comfort. It is about contamination, visibility, equipment stress, and power risk. If the wind is moving more dust today, then solar surfaces may perform worse. If dust concentration is high, optical systems may degrade. If an EVA route crosses an area where particles tend to collect or lift easily, the contamination cost goes up. So even though the Martian air is weak in pressure, it still has the power to make operations harder in ways that matter every day. And that becomes much more serious when you move from normal dusty conditions to actual dust storms. This is where Mars starts controlling the calendar. Dust storms on Mars do not need to tear structures apart to become dangerous. They only need to block sunlight and push dust into the mission faster than your systems can comfortably handle. Some Martian storms can become enormous and last for long periods. Regional storms can grow large enough to change operations across wide areas. And in rare cases, storms can grow to global scale. That matters because even if your habitat stays structurally fine, your power budget may not. That is what makes storms on Mars such a serious systems problem. A storm can reduce the sunlight reaching solar panels enough that power margins suddenly tighten. Then everything else starts reorganizing around that fact. You cut non-essential activity. You postpone outside work. You protect battery reserves. You prioritize life support, thermal control, communications, and only the most necessary equipment. What looked like a normal science and maintenance schedule can turn into conservation mode because the weather changed the power picture. That is a very important shift in how Mars feels. On Earth, weather often feels like a planning inconvenience unless it becomes extreme. On Mars, even without violent pressure or rain or oceans, weather can go straight into the core of survival because it affects light, dust loading, heat, visibility, and energy at the same time. A storm does not need to destroy hardware directly. It can just starve the hardware slowly by cutting the energy available to keep everything running comfortably. That is why the first 100 days are planned with dust storms in mind even before one happens. You do not wait to care about storms until the sky darkens. The whole power system, the activity schedule, and the reserve strategy are built around the possibility that Mars may suddenly cut down your available sunlight and force the mission into a narrower operating mode. That means weather is not a side issue handled by a forecast board. It is one of the things deciding how ambitious the mission can be on any given day. And after enough time on Mars, the forecast stops feeling like a support tool and starts feeling like part of daily survival. By the end of the first 100 sols, weather is no longer something you occasionally check. It becomes part of the culture of the base. Pressure drops are not just numbers anymore. They can hint that a vortex or dust devil is moving through the area. Changes in dust opacity are not just scientific observations. They affect power budgets, visibility, and EVA timing. Temperature predictions are not only useful data points, they define safe working windows. Seasonal pressure changes stop sounding abstract too, because you begin to understand that even the Martian atmosphere shifts over time in ways that affect operations. That changes the emotional rhythm of the mission. You start living by forecast the way sailors once did, because the environment is setting terms whether you like it or not. You learn to respect patterns. You learn what a bad trend looks like before it becomes a bad day. You learn that a small atmospheric change can produce a larger operational consequence later. And that is one of the signs that Mars is becoming real to the crew. It is no longer a destination with scenery. It is a place with environmental behavior that has to be watched constantly. The important thing is that this does not mean the mission is blind. Data from past landers and rovers helps a lot. Mars has been measured in much more detail than before, and that makes planning smarter. But better data does not make the environment gentle. It only makes the danger easier to describe and track. The planet is still cold in ways that stress hardware. The wind still moves dust in ways that affect every exposed system. Storms can still force a major change in priorities. Better knowledge does not remove that. It just means you understand the risk more clearly while living inside it. By the end of this stage, weather on Mars has stopped being a science topic and become part of the mission structure itself. It tells you when to move, when to stop, when to conserve power, when to protect systems, and when to stay inside. The atmosphere may be thin, but it still gets a vote in nearly every decision you make. And once the crew fully understands that, another truth gets harder to ignore. If the habitat is the only place where weather, pressure, and radiation stop controlling your body directly, then that habitat is no longer just shelter. It becomes the smallest functioning human world ever built. By this point, the habitat stops feeling like equipment and starts feeling like the only version of Earth you have left. That is the real change. In the first 100 days, the habitat is not just where you sleep. It is the system holding human life together on a planet that cannot support it on its own. That changes how you think about architecture. On Earth, a building gives you comfort, privacy, storage, and protection from weather. On Mars, a habitat does all of that, but it also has to take over jobs that the planet itself would normally help with. It has to hold pressure. It has to maintain breathable air. It has to control temperature. It has to keep water cycling. It has to support food storage, medical care, exercise, work, and maintenance. So the habitat is not a backdrop for the mission. It is the mission. That is why Mars habitat design matters so much. The first real human foothold on Mars is not going to be a city in any normal sense. It will be a small sealed structure with a few people inside trying to cover an enormous list of needs in a very limited amount of space. That means layout is not just a comfort choice. Workflow is not just an efficiency issue. Privacy is not optional. Exercise space is not a luxury. Medical capability is not a backup feature. Crop space, hygiene space, storage, repair access, and crew circulation all affect survival directly. Once you understand that, the habitat stops looking like a building and starts looking like a compact life system. And the strange part is that it has to do this while still feeling human enough to live in. That is where the real pressure starts, because every room inside has to do more than one job. In the first months, the habitat is never just one thing at a time. The same structure as your bedroom, your workplace, your kitchen, your gym, your clinic, your lab, your command center, your storage unit, and your shelter during environmental danger. Space is tight so functions overlap. One area may support work during the day and quiet recovery later. Another may hold equipment, maintenance access, and emergency supplies all at once. Even a simple open space inside the habitat has to be justified, because volume on Mars is expensive and every cubic meter has to earn its place. That creates a constant tension in the design. The habitat has to behave like a very reliable spacecraft because failure inside a closed environment can become life-threatening fast. At the same time, it has to feel stable enough for humans to keep functioning emotionally over long periods. If the layout is too cramped, too noisy, too awkward, or too stressful, performance drops, morale drops, privacy disappears, tension grows. But if the habitat is designed only for comfort and not for resilience, maintenance, and fault tolerance, then it becomes vulnerable in exactly the wrong place. So the habitat is doing two jobs at once all the time. It has to stop technical failure and it has to stop psychological erosion. It has to keep systems healthy, and it has to keep people healthy. That is why Mars habitat design is much harder than simply building a shelter and adding life support. The inside environment shapes the crew every day. It affects sleep, mood, routine, exercise, concentration, conflict, recovery, and trust. A bad habitat does not just feel unpleasant. It becomes a performance problem and then a mission problem. Then there is another layer that makes this even more serious. The habitat is not only threatened by the outside, it can also become dangerous from the inside if something behaves differently than expected. That is one of the least glamorous but most important truths about closed living on Mars. When people picture danger, they think about dust storms, radiation, suit failures, and surface hazards. But the safe place has its own risks because it is a sealed, engineered environment operating in partial gravity for a long time. Things that seem ordinary on Earth can behave differently there. Fire is a good example. Smoke movement, flame behavior, detection, cleanup, and material response can all change when gravity is lower and air circulation is tightly controlled. That means even a hazard humans understand very well on Earth can become less predictable inside a Mars habitat. And it is not just fire. Materials age, seals wear down, systems collect stress. Radiation can affect equipment over time. Small contamination problems can spread through an enclosed environment. A repair that would be simple on Earth can become serious when spare parts are limited and failure margins are tight. So the habitat is not simply a wall between you and Mars, it is a highly managed artificial world that has to stay stable under conditions humans have never lived through on another planet. That is why the phrase safe inside becomes more complicated on Mars. Inside is safer than outside, absolutely. But inside is also a technical environment with its own failure modes, and some of those are still not fully understood in long-duration partial gravity. So the crew cannot treat the habitat like home in the casual Earth sense. They have to treat it like a living system that needs constant attention. Air quality, filters, humidity, power loads, temperature, water recovery, waste handling, material wear, and emergency readiness all remain active concerns. The place protecting you is also one of the main things you have to keep protecting. And over time, that changes the emotional meaning of the habitat too. In the first days, it may still feel like a base you brought with you. By day 100, that idea is gone. By then, the habitat has become your atmosphere, your routine, your privacy, your sleep pattern, your meal space, your exercise space, your recovery space, your medical backup, and your only real separation from the planet outside. It becomes the smell you associate with safety. It becomes the sound level your brain starts recognizing as normal. It becomes the place where your body can stop fighting pressure, temperature, and dust for a few hours and just exist in a controlled environment. That is a deeper shift than it sounds. On Earth, home is connected to a larger living world. On Mars, home is the entire living world available to you. Outside the habitat is not a neighborhood, a landscape, or a wilderness in the normal human sense. It is a place where your body cannot function without support. So the habitat stops being gear and becomes civilization in its smallest possible form. It is where work happens, where law and routine exist, where care happens, where conflict has to be managed, where rest is protected, where maintenance keeps everyone alive, and where human normality is defended against a planet that does not provide any of it for free. That is why the first 100 days matter so much. That is when the habitat stops being temporary in your mind, becomes permanent enough to shape behavior. The crew starts organizing life around it instead of around the idea of returning quickly to Earth-like conditions. Habits form. Personal space matters more. Clean air, a stable temperature, familiar lighting, a place to sit, a place to eat, a place to be alone for a few minutes. All of that starts carrying much more weight because it exists inside the only environment on Mars where being human is physically sustainable, and that may be the biggest test of all. Mars is not only asking whether your structure can hold pressure or whether your life support hardware can keep running, it is asking whether a tiny artificial world can stay mentally livable while surrounded by a real world that is physically unlivable. The habitat has to keep the crew alive in the technical sense, but it also has to keep them recognizably human in the emotional sense. If it fails at either one, the mission begins to crack. By day 100, that truth is impossible to ignore. The habitat is no longer the place you are staying while you explore Mars. It is the place where humanity exists at that point in the solar system. Everything outside is risk. Everything inside is the fragile exception. And once you understand that, the next question becomes even more urgent. If the habitat is the whole human world on Mars, then what keeps that world alive every second of every day? Power. And if power starts failing, none of the other plans matter. The next hard truth is that none of your plans on Mars matter if the power system is weak. You can have a sealed habitat, working suits, stored food, and a trained crew, but if electricity becomes unstable, all of that starts failing in sequence. On Mars, power is not a background service. It is tied directly to survival. From the first day, almost everything keeping you alive depends on electricity. Air circulation depends on it. Thermal control depends on it. Water recovery depends on it. Communications depend on it. Computing depends on it. Medical hardware depends on it. Charging systems depend on it. Internal lighting depends on it. The machines that may eventually help you make oxygen or fuel from local resources also depend on it. So when people talk about power on Mars like it is just an engineering topic, they miss the real point. On Mars, electricity is part of life support whether you call it that or not. That changes the way the crew thinks about energy immediately. On Earth, a power outage is usually temporary and external help is close. On Mars, a serious power loss is not a disruption you wait out. It is the beginning of a systems emergency. If power drops too far, heating gets cut back, air handling starts narrowing, water processing slows or stops, batteries become harder to protect, communications may be reduced, non-essential equipment gets shut down, and the margin for any new problem gets smaller. If the loss continues long enough, the mission does not become uncomfortable. It starts moving toward failure. That is why the early mission is not only about landing safely and staying healthy, it is also about proving that the settlement can maintain stable energy flow day after day without slipping into a fragile state. Because once the base becomes power poor, every other choice gets worse, maintenance gets delayed, science gets cut, EVA planning tightens, resource processing slows, recovery options shrink. Power is the thing underneath almost everything else. That is also why solar power is both attractive and risky on Mars at the same time. On paper, solar makes sense. There is sunlight. Panels can generate useful energy. You do not have to carry fuel to burn in the normal sense. For some mission phases, solar can do a lot of work, but Mars has already shown the weakness in that idea very clearly. Dust gets involved. This is where the planet starts making the power system harder to trust. Solar arrays do not just have to deal with night. They have to deal with dust settling on them over time, and dust storms reducing incoming sunlight from above. That means the energy system is fighting two different losses at once. First, the panels can get dirty and perform worse. Second, the sky itself can dim and lower generation even if the hardware is otherwise fine. That makes every dust forecast into a power forecast too. A dusty day is not just a visibility issue. It's not just a maintenance issue. It is an energy issue. If airborne dust increases, solar performance can drop. If a storm develops, the margin can fall fast enough that the whole base has to shift into a more conservative mode. That is exactly why Mars can turn a normal operations day into a survival-focused day without breaking anything directly. It only has to reduce your available power. And that has already happened to machines we sent there. Mars missions that relied on solar power showed how difficult this can be over time. Dust accumulation can slowly drag performance down even without one dramatic event. Then a regional storm can push a system into safe mode because it no longer has enough energy to operate normally. That is a very important lesson for the first 100 days of a human mission. You cannot think of dust as one problem and power as another. On Mars, they're connected all the time. So the crew starts treating solar generation with the right level of caution. It can help a lot, but it cannot be the kind of system you trust blindly. You watch panel condition, you watch sky opacity, you watch battery state, you watch forecast trends, you watch whether energy income is matching the actual demand of the base. Because on Mars, the power system is not competing only with equipment loads. It is competing with the planet's ability to reduce sunlight whenever it wants. That is why nuclear power keeps coming back in serious Mars planning. Once you understand how much depends on steady energy and how vulnerable solar can be to dust, the appeal of continuous fission power becomes obvious. If you want electricity that does not care whether it is night, whether the air is dusty, or whether a storm has been sitting over your region for days, then fission starts looking less like an option and more like a very strong answer. And this tells you something important about what a Mars mission really is. It is not just a story about using local resources and living simply on another world. It is also a story about how much reliable power you can bring with you and sustain there. A strong power source changes everything. It gives you more heating margin. It gives you more water processing margin. It gives you more communications margin. It gives you more room for redundancy. It gives you more ability to run science hardware, support rovers, recharge suits, and process local materials into useful products. Reliable power widens the mission. Weak power shrinks it. That is why the first 100 days are really a test of whether your power architecture is robust or fragile. A short visit can survive on tight margins for a while. A settlement cannot. If you want the base to survive dust events, maintain healthy internal conditions, support long-duration work, run recovery systems properly, and keep future expansion possible, then energy has to be strong enough that the crew is not constantly making desperate trade-offs. You need enough for the normal day, enough for the bad day, and enough left over that one equipment problem does not push the whole outpost toward crisis. This is also where Mars corrects another common idea. People tend to think exploration is mainly about motion. Landing, driving, walking, drilling, reaching the next site. All of that matters, but the deeper truth is more basic. The mission only moves because something is staying stable in the background. If the whats are not there, the rest of the mission becomes irrelevant very fast. It does not matter how brave the astronauts are, how smart the crew is, or how impressive the hardware looks if the base cannot keep a stable flow of power alive on the surface. By day 100, the crew understands this in a very direct way. Power is no longer a line on a status screen. It is the condition underneath almost every other success. Stable power means breathable air keeps moving, heat stays where it is needed, water keeps cycling, communications remain dependable, and future capability stays open. Unstable power means every hour becomes narrower and more reactive. That is the difference between merely visiting Mars and actually beginning to stay there. And once power is stable enough, the next priority becomes even more important than comfort, science, or expansion. Because after air and energy, the thing that starts deciding whether humans can remain on Mars is water. Mars may still have it hidden underground, but in the first 100 days, every drop you recover, recycle, and possibly extract becomes more valuable than almost anything else you brought with you. By the end of the first month, water becomes more important than almost anything else on Mars. Not because it is rare in the abstract, but because every part of the mission depends on having enough of it in the right place, in the right form, at the right energy cost. That is the shift. Early Mars missions are not asking whether water exists there. They are asking whether humans can reach it, recover it, clean it, and build a settlement around it. That is one of the biggest changes in how people think about Mars. For a long time, Mars was treated like a world that used to have water but does not anymore in any practical sense. That is no longer the right way to think about it. Water is not missing, it is hidden. Ice appears to exist in many places below the surface, especially in some mid-latitude regions. Past missions already showed near-surface ice in some locations, and later mapping work made it much clearer that buried ice could matter directly for where future crews land. So once you are actually on Mars, the question stops being, is there water on this planet? The useful questions are much more specific. How deep is it? How clean is it? How much energy does it take to reach it? Is it close enough to the habitat to matter? Can you get it safely and repeatedly? Is the concentration high enough to build systems around it, or does it only look promising from orbit? Those are the real questions, because water on Mars only matters if it can be turned into a working part of the settlement. That means the first 100 days are not only about geology or exploration, they are also about resource reality. A map that suggests buried ice is exciting, but a settlement does not run on exciting maps. It runs on water that can actually be recovered, processed, stored and used without breaking the mission's energy budget. So water quickly becomes one of the main things that decides whether a landing site is just scientifically interesting or actually useful for long-term survival. But even if there is buried ice nearby, that does not solve your first month. The first water system on Mars is not mining. It is recycling. That is one of the most important operational truths of the whole mission. During the first days and weeks, the crew depends mainly on closed-loop water recovery. You are recovering moisture from the air, you are recovering water from hygiene use, you are recovering water from sweat and from urine processing. On Mars, that is not an efficiency upgrade. It is basic mission logic. A world that is hard to reach and hard to resupply does not allow casual waste, and that creates a major culture change almost immediately. On Earth, people are used to the idea that water comes in, gets used once, and then goes away into a system they do not think about. On Mars, that idea is gone. There is no used water in the normal sense. There is only water moving through stages of a loop. Once the crew starts living by that rule, the whole habitat changes. Every litre matters, every leak matters, every recovery percentage matters, every failure in the purification chain matters. This also changes how the crew sees their own daily routines. Breathing, sweating, washing, cleaning, cooking and waste handling are no longer separate from survival engineering. They are part of the water system. That means the most ordinary actions become tied to mission sustainability. If the recovery system performs well, the mission gets stronger. If it performs badly, the margin shrinks fast. Water is too heavy to waste, too necessary to ignore, and too central to every biological function to treat casually. That is why a high-efficiency recovery system is one of the most valuable technologies humans can bring to Mars. It reduces resupply pressure, it buys time, it stabilizes planning, it makes every stored kilogram of water go further. And in the first 100 days, that matters more than any big promise about future extraction, because closed-loop recovery is what keeps the crew alive, while the rest of the surface system are still proving themselves. Then, as the mission gets more stable, buried ice starts to matter in a bigger way, not only as a scientific discovery, but as the thing that begins to shape the future map of settlement. This is where Mars stops being just a difficult place to survive, and starts becoming a place where humans may be able to build something more permanent. If buried ice is accessible, it can support drinking water, it can support hygiene and agriculture, it can become shielding mass, it can supply hydrogen and oxygen for fuel production, it can widen the mission from a tightly limited outpost into something with more options. That is why local ice matters so much. It is not just a bonus resource, it is a multiplier for everything else. And once that becomes clear, geography on Mars changes meaning. A location is not valuable only because it looks interesting, or because it has dramatic terrain, or because it tells a good story. A location becomes valuable because of subsurface water access. That is a much harder standard. It means the future settlement map of Mars may be shaped less by beauty and more by hidden ice. The places that win may be the places where frozen water sits close enough to the surface in usable quantities near a terrain that still allows safe landing and operations. That also adds a layer to the mission. Once water becomes tied to where long-term bases should go, then prospecting is no longer just science. It becomes site selection for civilization. A crew looking for accessible ice is not only learning about Mars, it is helping decide where later crews can live, where infrastructure makes sense, where resource plants should go, and where a serious base could eventually grow. That gives water a much larger role than many people expect. On Mars, hydrology may shape settlement more than scenery ever will. And this is where the emotional meaning of water changes too. Until this point in the mission, Mars mostly feels like a list of things that make life harder. The air cannot support you. The pressure is wrong. The dust attacks hardware. The radiation keeps accumulating. The cold stresses every system. Power has to be protected constantly. Water changes the tone because it is one of the first places where Mars starts to look useful, not just hostile. That matters because water connects the planet's past and the mission's future in one line. Water tells you Mars was not always the planet it is now. It once had conditions very different from the ones trying to kill you today. And at the same time, hidden water suggests the planet still contains something humans can use to stay. That is a big shift. It means Mars is not just an empty dead surface you must completely fight against with imported supplies. It is a world that still holds some of the raw material needed for a human presence, if you can unlock it. That is why water becomes such a turning point in the first 100 days. It does not make Mars safe. It does not solve the mission. But it changes the question from how long can we endure this place to can this place help support us if we build the right systems? That is a much bigger question, and it makes the mission feel different. The planet is still dangerous, but now it also starts to look usable. By the end of month 1, that realization lands clearly. Mars still punishes the human body in almost every direct way, but under the surface it may be holding one of the resources that make staying possible. Not easy, not cheap, not automatic, but possible. And once you understand that, the next step becomes obvious. If the planet's air is mostly carbon dioxide, and the ground may hold water ice, then survival is no longer only about bringing supplies from Earth. It becomes about processing Mars itself. The air you cannot breathe becomes the air you have to industrialize. By the second month, the atmosphere starts changing role. It is still hostile to your body, but now it also starts looking like raw material. That is one of the biggest shifts in the whole Mars mission. In the first weeks, the air is something you hide from. By this stage, it becomes something you try to process. That change starts with a very simple fact. Mars has a lot of carbon dioxide in its atmosphere. For breathing, that is useless. For engineering, it is valuable. Once you accept that, the next step becomes obvious. If the planet gives you a sky full of carbon dioxide, then one of the smartest things you can do is build machines that turn some of it into oxygen. That is exactly why experiments like MOXIE mattered so much. It showed that the basic chemistry can work on Mars itself, not just in a lab on Earth. And that is a huge difference. A lot of ideas sound good in simulation. Mars does not care about simulation. What matters is whether the machine works in the real Martian atmosphere, with the real pressure, the real dust risk, the real thermal conditions, and the real operating limits of another planet. That is why even a small oxygen-making system was such a serious milestone. It proved that the atmosphere above the surface can be processed into something useful for human life. Not enough yet. Not close to enough. But real. That is the key point. The first lesson is not abundance. It is scale. This is where people can get the wrong idea very fast. Once they hear that oxygen has been made from the Martian atmosphere, it is tempting to think the problem is basically solved. It is not solved, it has only moved into a new phase. Making a small amount of oxygen is one thing. Making enough oxygen for breathing, reserves, emergencies, and possibly rocket oxidizer is a much bigger job. That is not a gadget problem, it is an industrial problem. A single astronaut needs far more oxygen than a small demonstration machine can provide. And if you are thinking beyond breathing, the scale gets much bigger again. A return mission would need a huge amount of oxidizer for ascent. That means the real challenge is not proving the chemistry once. The real challenge is running that chemistry at settlement scale, day after day, with enough power, enough reliability, enough spare capacity, and enough tolerance for dust, temperature swings, and wear. So in the first 100 days, one of the clearest realities is that local resource use is not magic. It is infrastructure. You're not pressing a button and becoming independent from Earth. You're beginning to build a chain of machines that has to work continuously under harsh conditions. The atmosphere gives you raw input, but turning that into breathable oxygen means compressors, processing units, power, heat control, storage tanks, maintenance, monitoring, and backup plans. It means engineering margin. It means industrial discipline. That is why this section matters so much. It forces a new way of thinking. Early in the mission, survival is mostly about protecting the crew from Mars. By the second month, survival starts becoming partly about using Mars. That is a major shift. Once you can pull useful oxygen from atmospheric carbon dioxide, even at a small scale, the atmosphere stops being just a threat. It becomes part of the settlement loop. Water recovery supports one part of the system. Oxygen production supports another. Ice, if it is accessible, may support both life support and fuel-related processes later. Waste streams start looking less like garbage and more like input. The whole mission begins moving toward a closed-loop mindset. And that is where Mars starts feeling less like a visit and more like a long-term engineering challenge. A short mission can survive by bringing almost everything from Earth. A real outpost cannot stay locked in that mode forever. The mass cost is too high, the dependency is too strong, the delay is too long. So eventually the settlement has to do more than consume supplies. It has to process local materials into useful products. Oxygen is one of the first and most important examples. That is why the psychological shift here is so big. Up to this point, most of the story has been about resistance. Resist the pressure, resist the cold, or resist the radiation, resist the dust, resist isolation. Now the story starts adding another layer. Use the planet where possible. Use its atmosphere. Use its buried ice if you can reach it. Use chemistry to turn a hostile environment into part of the support system. That does not mean Mars is suddenly helping you in any generous sense. The planet is still hard, still dry, still dangerous, still expensive to live on. But this is the point where the relationship changes. You are no longer only carrying a bubble of Earth through a hostile place. You are starting to connect that bubble to the planet around it through machines. That is a much more serious kind of presence. And this is also the point where Mars stops being just a destination. It becomes a site of industry. That is a much bigger statement than it sounds. For most of human history, exploration meant travel to a distant place and observation, maybe mapping, maybe staying for a while, then depending on home for almost everything important. Mars pushes past that model. Once you start making oxygen locally, even in small amounts, are doing something different. You're not just visiting, you're beginning to produce part of the conditions needed to remain there. That does not make Mars self-sufficient in 100 days, not even close. The early base still depends heavily on cargo, equipment, spare parts, stored supplies and planning from Earth. But something historic still changes. For the first time, humans may begin breathing in part because a machine on another world took that world's own atmosphere and reworked it into something the human body can use. That is a real threshold. And it also raises the stakes for everything else. If local oxygen's production becomes reliable, then power matters even more because the processing chain needs steady electricity. Water matters even more because it connects to other chemical loops. Maintenance matters even more because industrial systems cannot just be symbolic. They have to keep running. The habitat matters even more because now it is not only shelter, it is part of a small growing production network. Every system starts linking to every other system more tightly. That is why this stage of the mission is so important. It is not dramatic in the movie sense. There is no single big visual moment that explains it, but operationally it changes the future of the whole outpost. It means Mars is no longer only a place where humans can endure for a while using imported support. It is becoming a place where they may be able to manufacture some of what they need to stay. And once that starts, the mission stops looking like a stunt. It starts looking like the earliest version of a real off-world settlement. Small, fragile, limited, heavily dependent and still far from self-sufficient, yes, but no longer completely passive, no longer only defensive. It starts doing what civilizations do. It starts processing the environment around it. By the end of this phase, the crew understands something very clearly. The Martian sky is not for breathing. It is for industry. The air outside the habitat is still wrong for your lungs, still weak in pressure, still full of carbon dioxide. But with the right machines, some of that same air becomes oxygen, reserve capacity, and maybe one day propellant. That is not just a technical success, it changes what Mars is in practical terms. And once you begin using the air that way, the next pressure point becomes obvious. Survival is not only about air, water, and power, it is also about calories, nutrition, morale, and long-term health. Because even if your machines keep running, your crew still has to eat well enough to stay functional. On Mars, food stops being comfort first and becomes part of mission architecture. You can land on Mars with months of food and still not have a real food system. That is the problem. In the first 100 days, most of your calories still come from pre-packaged supplies brought from Earth. So at first, it can look like food is one of the simpler parts of the mission. The meals are already there. The menus are planned, the storage is organised. But that impression does not last long, because Mars turns food into a systems problem very quickly. The first issue is scale. A crew on Mars is not just eating to stay alive in a passive way. They are working in suits, doing maintenance, exercising to protect muscle and bone, managing stress, and adapting to a new gravity level after a long flight. That means energy demand stays serious. Some astronauts can burn up to around 3,500 calories a day depending on workload, and on Mars that matters because every calorie was heavy and expensive before it ever reached the surface. So the food system is not only about carrying enough mass, it is about carrying enough usable nutrition for long enough, in a form that stays safe and stable. And that is harder than it sounds. A Mars mission needs food that can last for years, when you include the trip out, the surface stay, and the possibility of delay. It has to keep its nutritional value over that time. It has to remain safe to eat. It has to be easy to prepare in a controlled habitat with limited water, limited waste capacity, and very little room for error. So when you look at the food stores on Mars, you are not looking at convenience meals. You are looking at part of the survival architecture of the base. That is why the first 100 days do not answer the question, do we have food? They answer a much harder one. Can this food system hold together under real Mars conditions without breaking down physically or psychologically? Those are different questions. You can technically have enough calories and still have a failing food system if nutrition degrades, menu fatigue builds, preparation becomes too inefficient, or crew morale starts dropping because every meal feels like the same lifeless routine. And that is where the next surprise comes in. Taste and morale matter much more than people expect. On paper, food can look like a numbers problem. Calories, protein, vitamins, shelf life, storage volume. All of that matters, but it is not the full picture. On Mars, meals are also one of the only recurring daily rituals that still feel recognizably human. The crew wakes up in the same sealed habitat, works in the same limited volume, sees the same people, hears the same machinery, follows the same maintenance schedules, and lives under the same delays with Earth. In that kind of environment, a meal is not just fuel. It is structure, comfort, routine, and one of the few moments in the day that can still feel normal. That is why monotony becomes a real threat. If every meal is technically sufficient but emotionally dead, the crew pays for it over time. Appetite can change, motivation can drop, and small frustrations can accumulate. Food fatigue sounds minor until you remember that on Mars there are very few other ways to break psychological repetition. A good meal does not solve the mission, but a bad food system can slowly make the mission harder in ways that spread into mood, patience, cooperation, and discipline. So the real question in the first 100 days is not just whether the food is edible, it is whether the food is sustainable for morale. Does the crew still want to eat it? Does it still feel varied and full enough? Does it give some sense of reward, rhythm, and normal life? Because if the answer starts becoming no, then food stops being a quiet success and starts becoming another background stressor in a mission already full of them. Then the stakes go higher, because food on Mars is not only tied to morale, it is tied directly to health in a much broader sense. By the time you're on the surface, your body is already dealing with radiation, altered gravity, confinement, sleep pressure, a changed schedule, limited freshness, and the general stress of operating in a closed environment far from Earth. Those stressors do not stay separate. They interact. The immune system can be affected by spaceflight conditions. The body can respond differently under long-duration stress. The habitat also has its own microbiological reality because people, air, surfaces, food handling, water recycling, and waste processing all exist in the same closed system. So now food is carrying another job. It is not only there to provide energy, it has to support medical stability. The nutrient profile matters, freshness matters, food safety matters, preparation hygiene matters, storage conditions matter. The balance of the diet matters more because the body is not operating under normal Earth conditions. If the crew starts getting less nutritional quality than expected, or if the food system becomes too dependent on heavily processed stability without enough variety, that can slowly become a health issue rather than just a morale issue. And this is where Mars forces another correction. Feeding people on another planet is not separate from keeping them medically stable there. It is part of the same problem. If nutrition is weak, recovery gets weaker. If food handling is poor, contamination risk grows. If the habitat microbiome becomes harder to control, food safety becomes more serious. If the crew loses interest in eating properly because the menu has become repetitive and unappealing, then performance can suffer in ways that spread outward into everything else. So by the end of the first 100 days, the mission is already learning something important. A Mars food system cannot just be efficient. It has to be biologically supportive, psychologically sustainable, and operationally realistic all at once. Anything less than that may still work for a short visit, but it will not support a true long stay. And that leads to the obvious next step. If pre-packaged food gets you through the beginning, what starts changing the future? Growing something. This is why crop space matters so much in Mars habitat planning, even before it becomes a major calorie source. In the early phase, plants are not there because they suddenly solve the food supply problem. They matter for more immediate reasons. Fresh food changes morale. Living growth changes the feel of the habitat. Plant systems may help support future recycling loops, and maybe most importantly, growing something proves that the base is moving beyond pure storage and into production. That is a huge shift. A habitat full of packaged meals is still basically a survival cache. A habitat that starts producing even a small amount of edible growth is becoming something else. It is becoming a place that can slowly reduce its total dependence on Earth. Not fast, not completely, but measurably. And that is why this stage matters so much. The first 100 days probably do not deliver agricultural self-sufficiency. They do not turn Mars into farmland. They do not free the crew from imported food, but they do force the mission to decide what it wants to become next. Is this outpost just a tightly managed camp running on stored supplies? Or is it the beginning of a place that can feed itself, even a little, and then more over time? That question goes deeper than food alone, because the moment you start growing part of tomorrow's meal, the whole mission changes. Water loops matter more. Lighting and power matter more. Waste processing matters more. Habitat design matters more. Human routine changes too, because now caring for living systems becomes part of staying alive. And psychologically that matters. It means the base is no longer only consuming what Earth sent. It is beginning to create. By day 100, that is the real turning point in the food story. Meals are no longer just something you opened from a packet. They are becoming evidence of what kind of settlement this might one day become. Mars does not let food remain a comfort issue for long. It turns food into logistics, health, morale, biology, and eventually agriculture. It turns dinner into infrastructure. And once that happens, the next tension gets even sharper. Because even if the habitat is stocked, the power is stable, and the food system is holding, the surface outside never becomes casual. Going outside does not turn into a normal walk. It stays what it was from the beginning. A tightly managed life support event where one mistake can still become fatal very fast. Going outside on Mars never becomes normal. That is one of the biggest corrections the mission forces on you. From Earth, the surface walk looks like the payoff. After months inside a spacecraft and weeks inside a habitat, Stepping onto open ground sounds like freedom, but on Mars, every EVA is still a high-consequence operation from start to finish. Even a short walk outside is built around limits. Suit status has to be checked. Battery margin has to be confirmed. Oxygen supply has to be tracked. Carbon dioxide removal has to stay inside safe range. Water and cooling have to perform properly. Thermal conditions have to be acceptable. Radiation exposure has to be considered. Dust exposure has to be managed. Navigation has to stay simple enough that a fast return remains possible if something changes. That means an EVA is not just going out to do a task. It is a carefully budgeted life support event with a clock running from the moment the airlock cycle begins. And the dangerous part is that the safe place can be physically close but operationally far away. The habitat may be only a few hundred meters behind you. On Earth, that would mean almost nothing. On Mars, it can mean everything. If your suit has a serious problem, if a mobility system jams, if dust fouls an interface, if you fall badly, if visibility drops, or if you start losing thermal control, that short distance can become very hard to close in time. That is why even a routine outside job stays serious. The margin is small and the consequences are immediate if the systems around your body stop doing their job. So by the time the first 100 days are underway, the crew stops thinking of EVAs as breaks from confinement. They start thinking of them as controlled risk events. Necessary, productive, often successful, but never casual. The surface is where exploration happens, but it is also where life support gets stretched farthest away from the habitat. That means outside work is always tied to the same hard question. If something goes wrong right now, how fast can we get back inside pressure? Then Mars adds another layer to the problem. The planet looks huge and open, but your real range is small. That is one of the strangest things about surface operations. You are standing on a world with vast plains, crater rims, channels, dunes, and horizons that make the place feel unlimited. But your actual operating radius early on is tightly constrained by life support, communications, terrain, dust, and return time. So the freedom is more visual than practical. You can see very far. You cannot safely go very far without bringing much more infrastructure with you. That is what makes Mars mobility deceptive. The surface feels like open territory, but early in the mission you are still tied to a small network of safe routes and known distances. Communications have to remain reliable, suit consumables have to leave margin for delays. Terrain has to be understood well enough that you are not surprised by a slope, a loose patch of regolith, or a surface condition that slows you down more than expected. Dust management matters too, because longer traverses can mean more contamination, more wear, and more cleanup burden when you return. And Mars has already shown through robotic missions that moving around there is hard even for machines built specifically for that environment. If powered flight on Mars required extremely careful engineering for a very light robot, then human movement in a suit is obviously not simple. A person on the surface is dealing with pressure systems, mass, balance, heat, dust, and limited consumables all at once. So even when the landscape looks inviting, the real operational picture stays narrow. In the first 100 days, Mars teaches you that a large planet does not automatically give you large freedom. That is why safe range becomes one of the main hidden facts of life on Mars. You may be standing on a world as broad as Earth's dry land, but in practice you are functioning inside a small bubble of reachable terrain. The map in front of you is huge. The map you can safely use today is not, and that makes local knowledge far more important than most people expect. Because once you start doing repeated EVAs, the surface stops being scenery and starts becoming intelligence. You begin noticing patterns that matter directly to survival. Where does dust collect after a windy period? Which route causes the most contamination on the way back in? Which areas give better footing in low gravity? Which slopes feel manageable at first but become awkward when you're carrying tools or samples? Which times of day give the best thermal window for outside work? Where do pressure drops and dust devil activity show up more often? Where does loose regolith slow movement enough to eat into return margin? Those questions turn into part of daily planning because Mars punishes generic thinking. The surface around the habitat becomes a place the crew has to learn in detail. not just as a map of landmarks, but as a map of hidden costs. One route may be shorter but dirtier, another may be cleaner but more exposed. One work window may have better light but worse thermal conditions. Another may reduce temperature stress but increase dust movement. In the first 100 days, the crew builds that local understanding through repetition, through small mistakes, through maintenance results, and through seeing which assumptions were wrong. That is when terrain becomes much more than ground shape. It includes contamination risk, visibility, traction, suit workload, return speed, and exposure. A patch of surface is not just flat or rough. It is easy or expensive. It saves margin or consumes it. And once the crew starts reading the land that way, EVA planning becomes much more intelligent and much less romantic. Mars stops looking like open exploration and starts looking like controlled movement through a field of penalties. That leads to the final correction in how outside work really feels. On Earth, a walk is mostly movement. On Mars, a walk is systems operation. When you step outside, you're managing pressure around your body, oxygen flow, carbon dioxide scrubbing, cooling, battery use, water supply, dust loading, tool control, navigation, and a return timer at the same time. And you are doing all of that while moving through terrain in 0.38 G on a body that is still adapting to Mars. So the act of walking itself is tied to constant monitoring. You're not just going somewhere, you're running a portable life support system while trying not to waste margin. That is why outside work never becomes mundane in the first 100 days. It may become smoother. It may become more practiced. The crew may get faster, cleaner, and more confident. But it never becomes casual. The same planet that looks like the ultimate frontier still forces every step to stay inside a chain of technical conditions. Forget one of those conditions for long enough and the surface becomes dangerous very quickly. By the end of this phase, the crew understands that an EVA is really an extension of the habitat, not an escape from it. The suit is a temporary pressure vessel. The route is a temporary safe corridor. The task plan is a temporary permission to be outside. None of that is freedom in the normal Earth sense. It is controlled exposure with good engineering. And once that becomes clear, the next strain on the mission starts moving into focus. Because even when the EVA goes well, even when the crew gets back inside safely, another pressure keeps building that cannot be fixed by just closing the hatch. The distance from Earth does not only change logistics, it changes conversation, decision-making, and the way the human mind handles isolation. By the second and third month, the silence between you and Earth starts changing the crew itself. You can survive the landing, stabilize the habitat, manage the dust, and still run into a problem you cannot fix with a wrench. Mars changes the way human conversation works. That sounds small until you live with it. Then it starts affecting judgment, stress, relationships, and the way the whole crew experiences distance. On Mars, talking to Earth stops feeling like talking. That is the first psychological break. Depending on where the planets are in their orbits, a message can take roughly 13 to 22 minutes to get there, and just as long to come back. At maximum separation, one-way delay can be about 22 minutes. So the simple rhythm of human exchange disappears. You do not ask a question and hear an answer. You send a message into silence, keep working, and wait. By the time a reply comes back, the moment that created the message is already gone. That changes the emotional meaning of communication almost immediately. Encouragement arrives late. Advice arrives after the decision is already made. Bad news does not hit in real time. Family conversations stop being conversations in the normal sense and become a chain of delayed recordings. Even ordinary things feel different. A joke lands late. A misunderstanding takes longer to fix. A disagreement has time to cool down before the answer shows up. Grief moves slowly. Relief moves slowly too. Nothing from home reaches you at the speed your nervous system expects. That is one of the first ways Mars rewrites psychology. Distance stops being something you measure in miles or kilometers. You start feeling it as delay. The gap between you and Earth is not just physical anymore. It is built into the timing of every human exchange. That matters because a lot of emotional stability on Earth depends on immediate response. You say something, someone reacts. You ask for reassurance, it comes back quickly. You explain a mistake, the other person answers in the same emotional moment. Mars breaks that rhythm. And once that rhythm is broken for long enough, relationships start feeling different even when they are still strong. So one of the first invisible changes in the first 100 days is that home becomes less interactive and more archival. Messages from Earth feel more like capsules arriving from another time state. They still matter. They may matter even more emotionally, but they no longer function like live support, and that forces the crew to build more of their emotional life locally, inside the habitat, with the same few people every day. That is exactly why isolation is not a side issue in Mars planning. It is one of the central hazards. A crew can have enough oxygen, enough water, enough food, and enough power, and still start losing performance if the psychological system begins to fail. That is the point NASA's long-duration isolation studies keep driving toward. Confinement is not just unpleasant. It changes how people think, sleep, react, and work together. Anxiety matters, low morale matters, sleep disruption matters, interpersonal tension matters. On Mars, those things are not separate from mission safety. They are part of it. And the reason is simple. The habitat is small, the crew is small, the mission is long. There is nowhere to really leave. There is nowhere to go cool off in private for half a day, unless the habitat design has created that option, and even then the social system remains sealed. On Earth, tension can often be managed by changing environments. You go outside, you take a drive, you spend time with someone else, you walk away from the situation. On Mars, the social environment is much more closed than that. If conflict builds, it stays in the same air, the same rooms, the same routine. That is why some of the most important work in the first 100 days may not look dramatic at all. It is the crew learning how not to grind each other down. It is learning when to step back, how to communicate clearly, how to share limited space, how to disagree without damaging trust, and how to protect routines strongly enough that the habitat stays emotionally stable. Those skills may sound softer than engineering, but on Mars they are part of engineering. A crew that starts emotionally fracturing becomes less sharp, less patient, less precise, and less resilient. That kind of decline spreads into maintenance, decision-making, safety discipline, and recovery from unexpected problems. Then Mars adds another pressure that sounds tiny in numbers but is not tiny in experience. The Martian day is close to Earth's, but not the same. It is about 24.6 hours long, that is close enough to feel familiar and far enough to matter. This creates a strange mental effect. Mars is not so different that your body completely rejects the schedule, but it is different enough that your internal clock has to keep adjusting. To stay aligned with the Martian soul, the body has to shift slightly later over time. That sounds manageable until you remember what depends on circadian stability. Sleep quality depends on it. Alertness depends on it. Mood depends on it. Memory and judgment depend on it. A crew operating under technical pressure cannot afford much drift in those areas. So the first 100 days are not only about missing Earth, they are about whether your body clock can stay synchronized to a world that is almost familiar, but not quite. Mars does not hit you with a completely alien cycle. It does something subtler. It keeps the rhythm close enough that you expect normality, then slowly pushes it off-center. That can create fatigue in ways that are easy to underestimate. A slightly off-schedule once is no big deal. A persistent mismatch between body rhythm, work demands, and environmental timing can become a real problem. And because the crew is already dealing with confinement, delayed communication, suit operations, maintenance load, radiation stress, and partial gravity adaptation, even a modest circadian strain matters more than it would at home. Sleep loss on Mars is not just tiredness. It can reduce patience, make judgment slower, and increase the chance of mistakes in an environment where mistakes are expensive. So by the second and third month, part of psychological survival is simply keeping the body clock, work structure, and emotional state aligned well enough that the crew still functions as a team. That leads to the deepest change of all. Mars does not only isolate you emotionally, it changes who has authority in the moment. Because of the communication delay, the crew cannot treat Earth as a real-time mission control the way astronauts in low Earth orbit can. If a system behaves strangely, If an EVA has to be cut short, if contamination shows up somewhere unexpected, if a power fault starts cascading, the crew cannot always stop and wait for a round-trip conversation before acting. They have to diagnose faster, decide locally, and accept the consequences. That is a completely different psychological load. At first, that sounds empowering. More autonomy, more responsibility, more direct control, and it is all of those things. But it also means there may be no faster, higher layer of human judgment available when the pressure is on. You can send the message to Earth, you can ask for analysis, you can compare notes later. But in the moment, if the clock is running, the crew is the authority. That changes the meaning of competence. On Mars, the crew is not just operating equipment, it is functioning as its own frontline decision structure. That means technical skill has to combine with emotional stability in a much deeper way. A person who is smart but panics is dangerous. A person who is calm but avoids decisions is dangerous. A person who is brilliant but cannot work inside a tight social unit is dangerous. Mars pushes all of that into one system. The crew has to think clearly, trust each other, and act without waiting for Earth to settle every uncertainty. So by day 100, one of the most important transformations is invisible. The crew has become more psychologically separate from Earth than any human expedition before it. Not cut off, not abandoned, but forced into a new kind of independence. Home still matters. Home still guides, advises, supports and watches. But home is no longer the place that closes the loop in real time. The crew closes the loop. That is the real mental threshold Mars creates. You do not just go far away. You start becoming the highest speed human judgment available to yourself. And that is a burden as much as it is an achievement. Because if a major problem starts unfolding, there may be no one else to hand it to quickly enough. By the end of the first 100 days, the silence between you and Earth has changed more than your routine. It has changed the structure of your relationships, the timing of your emotions, the way the crew handles stress, and the level of authority each person has to carry. Mars does not only test whether humans can live far from Earth, it tests whether they can remain mentally stable while becoming more psychologically self-contained than any crew in history. And while all of that is happening inside the habitat, Mars keeps doing something else outside it. While you fight to stay alive, the ground under your boots keeps revealing evidence that this world was not always this hostile. That may be the next big shock. The same planet trying to kill you now may once have had conditions that could support life. One of the strangest parts of living on Mars is that while the planet is trying to kill you in the present, it keeps showing you signs that it was not always like this. That changes the whole feeling of the mission. You're not just surviving on a hostile world, you're walking across evidence that this world used to be very different. The ground under your boots is the first clue. Places like Jezero Crater were chosen for a reason. Scientists think that area once had an ancient river delta and a lake. That matters because deltas do not form from one brief event. They form when water moves, settles, carries sediment, and does it long enough to leave a structure behind. So when humans move across that terrain, they are not just crossing rock. They are crossing the remains of a system that once had flowing liquid water stable enough to shape the surface in a way we recognize very clearly from Earth. And that is a big shift in perspective. Up to this point, Mars feels like a place defined by low pressure, toxic air, dust, radiation, and cold. Then the geology starts telling you that this same planet once had conditions that were much closer to the kind of environment we connect with habitability. Not proof of life, not proof that Mars was Earth-like in every way, but strong evidence that water once moved across the surface in persistent and organized ways. That changes every traverse. A walk to inspect equipment or collect samples is no longer just operational movement. It is also movement through a planetary archive. Layers of sediment, grain sizes, mineral patterns, and rock shapes start carrying a different meaning. They are telling you that Mars was once able to support lakes, rivers, and a much more active surface water system than the one you see now. And that matters because on Earth, places with long-lived water are exactly the kind of places where the question of life becomes serious. So the first 100 days are not only about staying alive on the current Mars, they are also about confronting the fact that the current Mars is not the whole story. The hostile world around you may be the end state of a much older and wetter planet. That makes the mission scientifically bigger and emotionally stranger at the same time. Then there is the next correction Mars gives you. Even now, the planet is not as dead and static as it first appears. For a long time, people tended to picture Mars as a frozen world that had basically stopped changing deep inside. But seismic data changed that. Mars still shakes. It still stores stress in its crust. It still experiences quakes and impacts. That matters immediately for a human mission, because the ground under your habitat is not just scenery or foundation. It is part of an active planetary body. That changes the engineering picture first. If the planet still has measurable seismic behavior, then infrastructure has to take the ground seriously. Habitat placement, foundation design, buried lines, storage units, and long-term construction all have to account for the fact that Mars is not perfectly still. Even if the seismic hazard is not constant and catastrophic, it is real enough to matter. A crew living there is not just dealing with the weather above and dust around. It is also living on a world that still moves below, but it changes the emotional story too. Mars stops feeling like a fossil. It starts feeling like a planet with an interior that is still active enough to surprise you. That matters because human beings respond differently to a world that is merely dead and a world that is still physically evolving. The second one feels less finished, less settled, less simple. It reminds you that the surface conditions you see are only one part of the planet's reality. And that connects directly to the chemistry story, which keeps getting more complicated, not less. This is where Mars becomes very hard to reduce to one clean sentence. It is not enough anymore to say it is a dead desert with some interesting rocks. The chemistry does not let you simplify it that way. Organic compounds have been detected on Mars, and that matters because organics are the kind of molecules that keep the question of past habitability open. That does not mean life was there. It does not prove biology. Organic compounds can form through more than one pathway. They can come from geology. They can come from meteorites. They can come from processes that have nothing to do with living systems. But that is exactly why the story gets more intense instead of less. If the chemistry were simple, the mission would become simpler too. It is not simple. Mars keeps presenting pieces that fit into multiple explanations at once. The organics do not let you say, case closed. They force you to say, we still do not fully know what happened here. And that changes what the first 100 days mean scientifically. The crew is not just trying to survive on a harsh world while collecting samples from a dead and fully understood place. They are operating on a planet that keeps preserving clues without giving the final answer. Every drilled sample, every layered rock, every chemical signature is part of that tension. Mars keeps saying there was once more going on here than the surface today would suggest, but it does not hand over the conclusion easily. That is one of the reasons the mission feels so different from a normal field expedition on Earth. On Earth, water, organics, and active geology are all the familiar categories. On Mars, the same categories are loaded with much bigger consequences because they connect directly to one of the oldest questions in planetary science. Was this planet ever habitable in a serious way? And if it was, how far did that go? Then the biggest answer Mars gives is not about what it might have had, it is about what it lost. This may be the hardest truth in the whole section. The reason Mars is so hostile now is not random. The planet did not just happen to end up dry, cold, and thin-aired for no reason. Over immense spans of time, it lost most of the atmosphere that once gave it a better chance of holding on to surface water. Atmospheric escape processes slowly stripped that protection away. Without enough atmosphere, the pressure dropped, the climate changed, and the surface became the harsh place you are standing on now. That means the first 100 days on Mars are happening inside the aftermath of a planetary collapse. You are not just visiting a cold landscape, you are living in the remains of a world that may once have had thicker air, more stable water, and a much better chance of supporting habitable conditions. The dry, low-pressure environment around you is not just a natural baseline. It is the end result of billions of years of loss, and that changes the scale of the mission immediately. Mars stops being only a destination and starts looking like a warning too. The thin air is no longer just an engineering challenge. It is evidence. The cold is no longer just a survival problem. It is evidence. The dry regolith, the buried ice, the exposed delta deposits, the damaged atmosphere, all of it points to a world that was transformed so severely that its surface became almost unrecognizable in biological terms. So while you are spending the first 100 days fighting for pressure, oxygen, power and water, Mars keeps telling a second story under your feet. It is telling you that planets can change so much that habitability itself can collapse, that they can go from having the ingredients for rivers and lakes to becoming near vacuum deserts, where humans survive only by carrying an artificial environment with them. By this point, that is one of the biggest mental shocks of the whole mission. You came to Mars to prove humans can live on another world, but the planet keeps forcing another question back at you. What happened here that made living so hard in the first place? That question is not abstract anymore. You are standing inside the answer. And once that sinks in, the next section gets even more serious, because by day 100, the crew is no longer asking whether Mars is impressive or dangerous. That was settled early. The real question now is whether all the systems are holding together strongly enough to turn a landing into something more permanent. By day 100, Mars stops being the destination and becomes the filter. By day 100, the big question is no longer whether humans reached Mars. That stopped being the main story the moment the landing worked. The real question now is whether the base is actually holding together as a living system. That is what Mars has been testing the whole time. At this point, everything becomes an audit. Is the power system still stable through night, cold and dust? Is water recovery still performing well enough that the numbers make sense long term? Are the airlocks and suit procedures staying clean enough that contamination is not slowly building into a bigger problem? Is radiation exposure still inside the mission limits? Is the crew still thinking clearly after months of delay, confinement, repetition and stress? Are the filters still doing their job? Are the habitat seals still clean and reliable? Is the food system still working not just in calories but in morale and health? Is exercise still protecting muscle and bone strongly enough that the body is not slipping backward? That is what Mars does by day 100. It turns exploration into an ongoing systems check. Every success now has to repeat itself. Once is not enough. Landing safely once is not enough. Running life support once is not enough. Completing one EVA is not enough. The mission has to keep doing all of it again and again without the whole chain starting to weaken. And if that chain does start weakening, then the mood of the mission changes very fast. It stops being a question of progress and starts becoming a question of how much time it is left before one problem forces everything else into crisis mode. That is the hardest truth of the first 100 days. You have not really adapted to Mars in the way people often imagine. You have not become natural there. You have not become comfortable there. You have not turned Mars into a second Earth. What you have done is build a working exception inside a place that still does not want to support your biology. That distinction matters. The pressure outside is still wrong. The atmosphere is still toxic to breathe. The radiation is still accumulating every day. The dust is still trying to get into seals, filters, joints, and machinery. The gravity is still low enough that the body may not be fully protected from long-term change. The weather is still capable of cutting into power margins and changing the whole schedule. None of that improved because Mars became friendly. It improved because the crew got better at resisting Mars with engineering, routine, discipline, and constant correction. So by day 100, the right way to say it is not that humans learnt to live normally on Mars. It is that humans managed to keep a fragile but functioning human zone alive there. That is a very different statement, and it is the more honest one. The base works because every part of it is being defended all the time. Power is defended, air is defended, water is defended, food is defended, cleanliness is defended, mental stability is defended, physical health is defended. Nothing important is left to the planet itself. And yet, if all of that is still working on day 100, then something historic has happened anyway. Because if the base is still running, then your species has done more than just visit Mars. It has shown that a human outpost can persist there for a meaningful stretch of time. Pressure has been maintained, water has been recovered and reused, food discipline has held, the crew has stayed medically and psychologically functional. Communications delay has been lived with rather than just simulated. EVA operations have been repeated in the real environment. The habitat has remained a working human space rather than collapsing into a failing machine. And maybe, even in these early stages, local resources have started entering the loop through oxygen production, planning for buried ice or other forms of in situ processing. That is a major threshold. It does not mean Mars is solved. It does not mean settlement is easy. It does not mean the risks are understood completely. But it does mean Mars is no longer just a destination humans can touch briefly in theory. It becomes a place where a human system can remain active, structured and self-protecting for long enough to prove that staying there is a real engineering problem, not just a fantasy. That changes the meaning of everything that came before. The landing is no longer just a stunt. The habitat is no longer just shelter. The suits are no longer just protective gear. The water loop is no longer just efficient recycling. The food system is no longer just storage. The oxygen machine is no longer just an experiment. The whole mission starts looking like the first rough version of something bigger. Not just exploration, but continuity. And that is why Mars changes category by the end of these 100 days. For most of human history, planets were objects in the sky, symbols, targets, or dead worlds. Mars becomes something more difficult and more important. It is hostile enough to reject your body almost completely, but structured enough that your machines can still work there. It is damaged enough to show what planetary loss looks like, but still rich enough to offer buried ice, useful chemistry, ancient water records, and the raw materials for industry. It does not welcome you, but it does not make persistence impossible either. That is what makes it so important. So the first 100 days do not end with a clean victory. They end with a much harder realization. You did not go to Mars just to stand on another planet. You went there to test whether human civilization can exist somewhere that does not naturally support it. And by day 100, if the outpost is still alive, you have your answer in the first real form that matters. Not that Mars is easy, not that Mars is ours, not that humans belong there already, only this. A human world, even a very small one, can be kept alive there. And once that becomes true, Mars is no longer just the destination. It becomes the first place that proved human civilization does not have to remain tied to one planet forever. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.